Good morning and welcome everybody to this new webinar from the Dipartimento di Scienze della Terra. You know, there is during the lockdown, our department organized several webinars on the most important topics about science, but also about this pandemic situation. So I'm really happy to have with us as the last webinar for this year's academic year. Of course, we will start again at the end of September. I'm really happy to have with us Neil Roberts. Neil Roberts, it's, in my opinion, or at least it is for me, one of the most prominent scientists in studying the climatic evolution of the Mediterranean, in particular regarding the Holocene, and also as a really prominent researcher on the impact of climate over civilization in the Mediterranean. So I think Neil Roberts represents a sort of light for many of us who study the climatic evolution in the Mediterranean. And he comes from the University of Plymouth. Is now the editor of Journal of Quaternary Science. And many of you probably know Neil for the very famous books on the Holocene, which is, of course, in many libraries, and many of my students, but probably others studied on this book about the Holocene. So, and today we'll tell us about something about Holocene climate and civilization. And let me say, this meeting has been organized, this webinar organized also with the support of the Center for Study of Climatic Change's Impact from the University of Pisa, and we have the pleasure to have the president connected somewhere. It's Giacomo Lorenzini, Professor Giacomo Lorenzini, but also this webinar is also organized with the support of Italian Association of Quaternary. And there is the president now with us, and after my end, I will pass for very few words of welcome from him. And just some technical points for all the people. Please switch off your microphone and camera to increase the connection. And at the end of the presentation, there is room for questions. Please, you can see if you are connected with the Teams, there is the possibility to pre-note, to book the questions using the hands in the toolbars. Or maybe if there is no so much busy, you can send a message on using the same system, or in case you can switch on your microphone and ask the word. So, but this please at the end of the presentation. So switch off microphone and video in this phase. There is also a lot of connection also on YouTube now, and for the people on YouTube, they can also ask questions. They can write and we can read, and then we can pass the question to the relator. So I'll pass now for a short welcome to Giovanni Monegato, the president of the Italian Association of Quaternary. Please, and then please, Giovanni, pass you to Neil Roberts.
Okay. Thank you, Gianni, for the initiative, which is very appreciated. I'm pleased to promote as IQA, the Italian Association of Quaternary Study, the seminar of Professor Neil Roberts. IQA is now planning a series of initiatives on the road to the INQUA Congress Rome 2023, whose theme is Mediterranean Perspective on Quaternary Sciences. And we wanted to stress and support the point of view of quaternary studies, because the recent past can tell us so many things about our future and Earth futures. And in this perspective, I think this webinar is remarkable for the team, and I wish everybody to enjoy and take home his important message. Thank you, Gianni, and I pass the word to Professor Neil Roberts.
Right, thank you very much, both of you. I'm speaking. If you can't hear me, please let me know. I'm obviously delighted to be joining you. I'm in Oxford, in England now, which is where I'm living. I'll try and speak with a PowerPoint presentation for 35, 40 minutes, and then we can maybe have some questions. So I'm going to try and share that with you if I can manage to do that. Share the desktop. Hide that. Whoops, switch that off. Okay. Okay, let me just check again that. Okay, Jenny, can you hear me okay?
Yes, yes,
Fine.
please.
Okay.
Sort of wonderful, wonderful. It's okay.
Okay, fine. So I'm just going to talk through this. I can't see you, so if something goes wrong, then just please shout and let me know.
For sure.
Jenny asked me to talk maybe about climate change in the Mediterranean and its relations to past human history. So I've put together a few slides on really asking a question, and it's in the title. It says boon or curse. That's really a question of whether climate change has had a bad adverse effect, or how far it's actually also acted to stimulate human initiative and evolution. So I'm going to pick up a couple of major themes. So first of all, I'll kind of outline what I've called a climate population paradox. And I'll come back to that again at the end with a simple model to try and maybe look at relations between climate and human population. And in between, I'll elaborate a bit more, particularly about the Bronze Age period as a kind of testing ground. And I'll also explore some of the methodological issues about how we can examine relationships between particularly abrupt climate change and human adaptation, and how far lags and leads are important within that, and how far we can test that. Okay, so I'm just going to start with something very obvious, and this is a kind of summary of global population. We, of course, don't have a record of global population directly, so we have to reconstruct it either through modeling, which is what you see in the top slide here, two different models, the Hyde model and the KK10 model from Jed Kaplan, and whether it's using that or some proxy, there is, of course, no question that human population has increased globally during the course of the Holocene. Part of the reason for that has been the spread of farming, and farming began early in the Holocene in several different parts of the planet, and then spread out to replace other economies based on hunting and gathering and foraging. And the bottom graph is from an archaeological synthesis of global land use trends that was published in Science last year, which some of you may have seen. And you can see in that particularly in the late Holocene, the last 4,000 years or so, there's been a big increase in the area globally under agricultural land use or use for grazing animals, for pastoralists. So some of the explanation for the increase in population has simply been due to the global expansion of farming into areas that were formerly reliant on hunting and gathering, where much more of the natural vegetation could stay in place. But even if we take, even if we exclude that and simply look within areas, and I think I saw, I certainly saw Martin Finney, and I saw an Erica, so I'm not sure if this is which Erica it is, but if it's Erica Viberg, then she'll recognize this slide, which is a synthetic population reconstruction for southern Greece from the Peloponnese, using two different data sets, one from archaeological site survey and the other from numbers of archaeological radiocarbon dates, which I'll talk more about a bit later. And this covers the time period from the beginning of farming at the beginning of the Neolithic to the end of the Bronze Age, about 1000 BCE. And what you can see from that is that overall, within that defined area, there's been an upward trend. So the suggestion is that it's not simply the expansion of farming to different parts of the world, but also within areas that populations have also increased. If we then relate population change to climate, the relationship we would expect to see is one in which a favourable climate, and we can discuss what a favourable climate is, but particularly for farming, so a climate which is suitable to get higher crop yields or support more livestock and therefore increase the food supply, should allow population to grow. So in the scenario here, you see a well-fed cow. If you have a situation in which you have adverse climate change, so you have a drought event, for example, then the expectation is that would decrease food supply. You would end up with cows looking like the one in the photograph there. And if you don't have the food supply, there will be impacts on human population. So there's likely to be a demographic decline or possibly even a collapse. And in the diagram on the left, the population, I've just superimposed some of the well-known abrupt climate events during the Holocene, 8.2 Ka, 8.5 or 8,200 years ago, 5.5 to 4.2, 3.2. These are well known from the literature, whether they're global or single events are a matter for debates. But you can also see that on that graph, there is some indication that those periods of adverse climate change, abrupt droughts, were associated with falls in population. You can see the red line going down in pretty much all of those four dry events. It's not just in the kind of Neolithic and the Bronze Age that this explanation has been used. It's also been applied to historic times. The book on the top left by the American historian Kyle Harper, for example, called The Fate of Rome, you may not be able to see the subtitle at the very top, but it reads Climate, Disease and the End of Empire, End of an Empire, and it's clearly the Roman Empire. And he and some other historians and archaeologists have in recent years argued that particularly the end of Imperial Rome was triggered by environmental factors, including a deterioration in climate from the so-called Roman warm period. And various authors like Ulf Buntgen, for example, have identified a period, particularly in the 6th and 7th century CE, when there was relatively cold climatic conditions, and they've labelled this the late antique Little Ice Age. So for historic times too, people have argued that the same relationship would apply between climate and population. If you have an improving climate, population should increase, and if you have a deteriorating climate, then population should fall. And yet, what we know from the climate record is that certainly in Eurasia and Africa, the climate overall during the Holocene has become less favourable, not more favourable for human population. We recognise that, for example, in terms of global temperatures through the early to mid climatic optimum. And the diagram at the top right is a synthesis done a few years ago. A more recent one was published a month or two ago by Darrell Kaufman and colleagues. And it shows that between perhaps 10,000 and 5,500 years ago, proxy data indicate temperatures slightly higher than they are today, or that they have been in the late Holocene, and there's a climatic decline in temperatures during the mid-Holocene period. There is debate about how far that's a global trend. Some of the climate models find it hard to simulate, but nonetheless, there's a lot of empirical proxy climate data which indicates that summer temperatures in particular have cooled. And if you're living in parts of the world in higher latitudes, so in Scandinavia, for example, then cooler temperatures should mean less favourable conditions for growing crops. If you're in the Mediterranean, then high plateau, for example, the Meseta in Iberia, the Anatolian Plateau, or high mountain areas such as the Apennines in Italy, all those mountain regions should have become less well suited to farming. Farming should have become more difficult as the temperatures cooled. Even more important is the role of precipitation change, and we can see that, let's go back one. We can see that in the bottom left slide here, and this shows the isotope record from Kunf Cave in the south of the Arabian Peninsula, the work of Dominic Fleitman. The graphs I'm showing, as many of you will realize, sometimes run from the left to the right, and that's the case with the diagram in the top right, the temperature graph, and I've put an arrow on to show time. And in the cave isotope record, which is a record of moisture availability, of precipitation, the time runs from right to left. I'm afraid there's no standard in the climate community for that, so you'll have to keep an eye open for that, but I have put some arrows in to help. But again, the same time period between about 10,000 and 5,000 years ago, there was an enhanced monsoon. It's very well recognized in the Indian Ocean sector, so in South Asia and India, similarly in much of Africa and parts of East Asia as well. And many of those areas, for example, in the Indus Valley, saw the rise of complex civilizations, an increase in population, but they did so at the time when the climate had passed the early to mid Holocene optimum of warmer temperatures and greater moisture availability. So the precipitation trend and the temperature trend are going in the opposite direction from global human population levels. If we now move to the Mediterranean, which is the focus of the talk I'm giving the presentation today, we can look at the pattern by regions. And I saw Martin Finney has joined the meeting. So Martin will recognize this because this is a synthesis that Martin and I and various others, Boon, put together and published last year. Just to explain, it used around 40 records from cave isotopes and other climate proxies, from lake data, some marine data. It didn't include pollen because we were trying to compare climate against vegetation and land use, and that meant that pollen had to be kept separate as a response variable rather than being included in the climate reconstruction. and a series of regions there running from west Mediterranean and Iberia through to the east and the Levant. And that's the mean value there. I haven't put on the ranges, but you can see those in the published version. But if we look at that, then the area highlighted in blue there shows that in the eastern parts of the Mediterranean, the Levant, Anatolia, also in the southern part, that's to say in North Africa, in the Maghreb, that means areas like Morocco and Algeria, a clearly identifiable early Holocene wetter phase at about the same time as the enhanced monsoon was expanding over Africa and Asia. Not monsoonal rains in the Mediterranean, but there was an increase in moisture availability at the same time. That's also evident in climate model simulations. The one for the Eastern Mediterranean is shown at the right-hand end and the Western Mediterranean at the left-hand end. That's from the simulation that was published by David Brayshaw, colleagues some time ago now. And in the central Mediterranean, areas like the Balkans and Italy, there is some evidence that there was also a wetter period, but probably not as long in duration, maybe between about 8,000 and 6,000 years ago. And once we move to Iberia, then it's not really identifiable at all. If anything, Iberia seems to suggest the wettest conditions were in the mid-Holocene between perhaps 7,000 and 3,500 years ago. Most of those Iberian records come from the northern half of the Iberian Peninsula, in places like the Pyrenees. So again, we've got the same pattern in not all, but most of the Mediterranean, showing wetter conditions during the first half of the Holocene and then getting drier. So if we then compare the climate data against the population for the same region, and this is now Greece, so the Peloponnese archaeodemographic curve compared to the mean climate Z-score. Sorry, I didn't explain that the way we compared those different proxies was to convert them to Z-scores so that we had a common currency. There are lots of ups and downs and bumps and peaks and troughs in those records, but the overall uptrend in population is upward in Greece, and the overall trend in climate is from wetter to drier. So that raises the question, I think, about whether we've got the climate population relationship the right way round. Did in fact climate play a role not simply as a negative factor in decreasing or increasing food supply, but also in stimulating long-term societal transformation by stimulating innovation and maybe therefore leading indirectly to the emergence of complex state-based societies and civilizations during the Bronze Age. If we look at climate population relations in the Neolithic, I think there the relationship is a more straightforward and simpler one in smaller scale peasant type economies. If you've got subsistence farming, then crops are going to be vulnerable to frost and drought. And I think it's not surprising that there is often a relationship that we see in the evidence between favourable climatic phases and evidence for an expansion of Neolithic populations. This is a slightly fuzzy slide. It runs from right to left, but it shows again the data for Greece. And the blue curve shows the same climate Z-score that I showed you a minute ago, but it's now going right to left rather than left to right. And the other two curves, the orange and the grey one, are estimates of human population from numbers of archaeological radiocarbon dates, the so-called summed probability density functions. And they're separate from northern Greece, which is the orange curve, and grey, which is southern Greece. And you can see, I think, in that as the climate improved after about 9,000 years ago, that coincided with the expansion of the first Neolithic farmers into Greece, and that favoured food production and seems to have allowed relatively high levels of human population to be supported. Interestingly, as the climate then deteriorated after about 6,000 years ago, so too did the population. So there's a match in the subsequent bust period after the boom. There's a kind of bust period when there's actually quite a marked gap in the archaeological record. And that correlation between climate and population continues through till perhaps sometime in the early Bronze Age, perhaps 4,500 years ago. But then from then onwards, the bar that's shown in orange on the slide, there's really no relationship. So once we move into the Bronze Age, then the relationship between climate and population seems to break down. Now, if we were to look at this as a series of cycles, long cycles over time, if you have a pattern in which population increases, say during the Neolithic cycle, during favourable climatic conditions, and it then declines during a deterioration, the expectation is that you'll have a kind of correction to the population overshoot, and it'll return to something like the same base level. And when the cycle starts again, it ends up being essentially a repetition of the previous one. So in this case, you've got what I've called non-adaptive demographic cycles. However, that's not what we in fact see in the archaeological record. What we actually see is that the next cycle has a new baseline, and that population was able to rise to levels that were higher than in the previous cycle, because presumably the population carrying capacity had changed. So something has changed, something has happened following that late Neolithic crisis. Some societies have suffered and gone back to a much smaller population and a simpler level, but some have also responded in new ways by innovating. And the kinds of innovation that emerged during this period prior to the Bronze Age are quite varied. They include developments of secondary products. This is a label, an idea that was first put forward many years ago now by the late Andrew Sherratt, what he called the secondary products revolution. The secondary products allowed increasing trade and therefore interconnections between different regions, and also new technologies like irrigation. And those changes changed the nexus between population and climate and moved things to a new and higher baseline state. So one and probably the clearest example of this is what happened in the Northeast Sahara. These are data from Stefan Kropala and Cooper, which were published 15 years ago now. But there was a very clear African humid period in which turned much of the Sahara relatively green. And the map in the bottom left shows the distribution of archaeological sites during that African humid period. And as you can see, they were very well dispersed right across what is today a very dry desert landscape. As the climate deteriorated between 6,000 and 5,000 years ago, and the monsoon rains shifted south, so the Sahara was created, the dry lands expanded. But what's interesting was that there were several different responses by the human populations that had previously occupied that land. 3 different choices were made. Some people decided to essentially keep the same economy that they'd had previously, essentially based on cattle cultures, and they tracked their prevailing grassland habitat by moving south into the area where there was still rains and still grazing for their animals. So this helped encourage a kind of southward shift into sub-Saharan Africa, and what became the first of the sub-Saharan cattle cultures. A second adaptation involved people staying where they were, but the climate had changed, the resources were no longer the same, and so they had to adapt, and they adapted by adopting new nomadic lifestyles, no longer as sedentary, or they became more mobile, they became more focused around oases and ultimately around different livestock, including cattle, including camels. But the third, and in a way the most important and interesting innovation, was the populations that moved out of the desert and into the Nile Valley, which was a long linear oasis where there was abundant water. And there they lived in much higher population densities, and they developed new forms of food procurement through irrigation. And ultimately that shifted the population baseline in Egypt substantially upwards, and within really a very short space of time, a few centuries, we saw the emergence of the first civilizations in ancient Egypt, with pyramid building and the early dynastic civilizations. In other parts of the Mediterranean, there were other adaptations, and this is one which will, I hope, interest particularly Gianni Zanchetta, as somebody who I know keeps many olive trees and is very much involved in growing and harvesting the olives. And the olive is, of course, perhaps the most quintessential of all Mediterranean crops, along with the vine and some other tree crops as well, very important part of Mediterranean agriculture. And we see the emergence of the first, I think, truly Mediterranean farming systems coming in this second post-Neolithic cycle. And we see the earliest evidence for that in the Levant, with pollen evidence, pollen and archaeological evidence in the Chalcolithic cultures of the southern Levant, the Grasulian culture, from as early as 7,000 years ago. And the graphs there, which run from right to left, show the percentage of olive pollen in 3 pollen diagrams from the Levant, Lake Hula, the Sea of Galilee, and the Dead Sea. And they all show pretty much the same time an increase, very substantial increase in olive pollen at that time. Now, clearly olive is a wild tree as well as a domestic one. And what we may be seeing here is a response of the natural vegetation to a drying climate, but one which was then exploited and transformed further by human populations. I think there's no question that even if some of that olive pollen is coming from wild trees, the majority of it was by 6,000 years ago was coming from cultivated trees. We see that in archaeobotanical evidence. Some of the archaeological sites where this is important lie outside the natural range of wild olive trees in any case. And by 5,500 years ago, that olive cultivation had expanded across other areas of the Eastern Mediterranean, to Anatolia and to Greece. And it allowed expansion of farming into lands that had previously been unsuited to annual crops like cereals. And so the area of productive land also increased. So it raised the baseline for food production. It allowed increasing production of secondary products, in this case olive oil, which could then be grown on a more commercial basis and traded. I've looked so far really at the long-term trajectory of climate, but obviously during this period, particularly in the Bronze Age, there's been a lot of interest in abrupt climatic events, and I mentioned some of them earlier on. One sometime before 5,000 years ago, another around 4,200 years ago, and another sometime just before 3,000 years ago. They're marked there in the green bands. And it is very striking when we look at the archaeological record, particularly in the Eastern Mediterranean, that those coincide with changes in archaeological cultures. So this is not population per se, It's changes in material culture which are used to characterize and identify different archaeological periods. But for example, the 4.2K event essentially separates the early Bronze Age from the Middle Bronze Age. The 3.2K event separates, in many regions, the late Bronze Age from the beginning of the Iron Age. So there is, I think, a strong suggestion here that these abrupt events, climate events, acted as shocks to different cultures, different societies, and may have acted as a pacemaker for cultural change. That's not to say that they were the sole explanation or indeed even the ultimate explanation, but it does suggest that they played a role in the timing of cultural change. Well, I can't do a presentation to a mainly Italian audience without including at least one slide from Italy. So here is my Italian slide, and it's, of course, from records that'll be familiar to a number of you, particularly to Gianni, the cave Speleothem records from not very far from Pisa and Lucca in Coccia Cave and Ranella Cave. The time is running from left to right here, and these are the oxygen isotope records. And in the bottom of this graph is reconstructed population from archaeological radiocarbon date PDFs. So this was put together by Alessio Palmisano as part of a paper which is in review covering the whole of Italy. Just to highlight that in this graph, the population curve is the thin green line, but there's also a broader grey line, which is the envelope for 95% probability or uncertainty in terms of overall population expansion, so that the most statistically significant periods are the ones lying outside that envelope, and they are highlighted by the blue and pink bars. So that there are, for example, pink vertical bars during the early Neolithic, just after about 7,500 and 7,000 years ago, and another one about 3,000 years ago. And there's also blue bars marking periods which are below the expected envelope. For example, in the Middle Bronze Age, just before 3,500 years ago, and also some other periods, for example, in the Mesolithic. So we can compare two of the best climate records for archaeodemography, and this is, I should add, just for central Italy, so it's the same, more or less the same region. And what I think we can see there is that although there's no simple, clear relationship between the two, if there were relationships between climate and population, then they appear to have been lagged. In other words, the period of early Holocene moisture in Coccia Cave, which we can see from perhaps just before 8,000 years ago until perhaps 7,000 years ago, it's only the latter part of that which coincides with the population increase at the start of the Neolithic, when the first farmers reached central Italy. By the same token, the 4.2K event, and Gianni will certainly recognize this slide of a flowstone from Ranella, and the white band with the orange circle around it is the section which corresponds to the 4.2K event, although in that cave it's actually of quite long duration, apparently, sort of 300 to 400 years long. But if it does relate to population, of human population and the population decline in this area, it was different in other parts of Italy, but in this area actually occurred a couple of centuries later. And what's more, there are events in the population which don't have any equivalent in the climate record at all, that one can identify. The population peak at the start of the Iron Age, for example, it's really hard to see anything equivalent in the proxy climate data. So one of the questions here is would we expect population and archaeological cultures to respond instantly, or would we expect them to respond after some delay. I think one thing we have to be careful of in that regard is the danger of correlating our climate records too widely. And I've just put in one slide from the paper with Martin Finney, and this is the mapped synthesis of climate Z-scores from one particular 200-year time window. We integrated the data into 200-year time steps. So they don't identify abrupt events particularly well, but it was a way of combining different data sources and then enabling them to be compared against population and archaeology. So this is the time interval between 3,000 and 2,800 years ago. And we can actually see a very clear pattern for that time interval. This was probably one of the driest parts of the times of the Holocene in the Eastern Mediterranean. There are lots of brown triangles which indicate Z-scores below the long-term mean in the Levant, in Anatolia, and in Greece. But if we move into the northern part of the Balkans and Italy, then not all but many of the sites actually show an opposite trend. And I think this does highlight the risk of correlating between records on assuming that they're going to show the same thing, because sometimes they won't. And I'll just divert for one slide just to set out a very sort of simple schematic on how we might the different kinds of relationships that might exist between a cause, in this case climate change, and a potential effect or response, in this case in terms of the archaeological record. Very often what we do is we take two records, say of population, human population, from archaeological site data and climate proxies, and if we find that they correspond in time and they're synchronous, then we would tend to infer some causation, or at least infer that causation was possible between the two. However, as I indicated with the Italian data, sometimes it shows a lagged response. So the question is, does that mean that A could have caused B? Well, perhaps it could, but it clearly depends on how long the time lag is. Time lag perhaps of 100, 200 years in population might not be surprising. A lag of 500 to 1,000 years would clearly, I think, not be viewed as a reasonable, viable explanation. What we can say, however, is if the cause, in this case climate, occurs after the effect, in this case the archaeological record, then that time offset effectively falsifies the hypothesis that climate caused some kind of response. What this means is that getting the correct serial relations for hypothesis testing is absolutely critical. And that applies particularly to abrupt events such as the 4.2K event, which has had a lot of attention. Harvey Weiss kicked off this with his work at Tel Leilan in northeastern Syria, and he saw site abandonment after the great Akkadian Empire, and he found some evidence on site, but the most persuasive evidence is actually quite a long way away. This is from the Gulf of Oman, so it's actually several thousand kilometers away. In this case, a Marine Corps record showing a big peak in dolomite, indicating aridity at the same time. But clearly, testing whether the climate change and the cultural change were really synchronous is critically dependent on chronology. And there is a real risk of the phenomenon first named, I think, identified as such by Mike Bailey, what he calls suck-in and smear, with calibrated radiocarbon ages in practice creating statistical uncertainties of usually several hundred years, not just between dates, but between interpolated ages as well. And clearly that means that two events that may appear to be synchronous may actually have been out of sync, or events which appear to be out of synchrony could actually have been the same thing. So one of the questions is how can we improve on those correlations, and particularly how can we try and avoid some of the problems that I think are inherent in radiocarbon dating as forming the basis for correlating between records. So I'm just going to highlight two. One of them, again, will be familiar to quite a lot of I think of you watching, and that is the use of tephra layers. This shows the distribution map for the Santorini Tephra layer. The island of Thera, Santorini in the Aegean, erupted explosively during the Middle Bronze Age, the early part of the second millennium BCE, and it dispersed ash in a southward and eastward direction. You can see the isopatch maps there, and you can also see a number of sites where the tephra has been recorded either visibly or as a cryptotephra. It was also picked up in the inferred climate record from Central Anatolian tree ring widths, work done by Peter Kuehneholm, which he dated to 1628 BCE. This is one of our sites in Turkey, a shallow lake at a site called Gölhisar, and the Santorini Tephra layer was found there as a visible layer, a couple of centimeters thick. The core site lies on the edge. That core site lay on the edge of the lake. There's an archaeological site as a promontory in the lake. And the pollen diagram from the core site showed a very clear phase of human land use with tree crops like olive. And it began just a little bit after the Santorini Tephra layer. So that meant that it was possible to tie that cultural phase to the tephra layer and the well-dated tephra layer reasonably precisely. It began a little bit afterwards, but it's most likely to have begun that human land use phase in the late Bronze Age. It certainly, for example, isn't Hellenistic or Roman or date, and equally it's not early Bronze Age because it's after the Santorini Tephra. Similar example, this is again from Italy. This is Michel Magny's work at Acesa, which found tephra layers, the Avellino tephra, and then another tephra layer. And he was then able to use those to tie that to the lake level record and to the climate changes around the time of the 4.2K event. So one way is to use tephra. A second way that I think is potentially very powerful, and which we've sought to adopt, and which a number of other people, I saw Laura Sodori earlier on, and she and others have used this in Lago di Pergusa in Sicily, is to use the multiproxy approach, where you take different indicators from the same stratigraphic record. So in this case, we're looking at stable isotopes, that's a climate record and pollen, not as a climate signal, but as an indication of human land use. And this is from Crater Lake site in Turkey, which we've worked at, called Nile Lake. And it's dealing not with the Bronze Age now, but with later time periods. This is the late antique periods, late classical period through to medieval and modern times. And on the left, we've got some summary pollen data, tree crops like olive in green, cereal pollen in orange. And on the right is the total proportion of tree pollen, that's the green shaded area. And the blue curve is the oxygen isotope record from the same core. Now, the point about that is that there's no possibility of mismatch, no possibility of miscorrelation. Even if the ages are wrong, they must be of the same date. The pollen and the isotopes must be the same age, and therefore we can look at the sequencing between them and therefore do some hypothesis testing. So in this case, what we see is that there's a period when tree pollen increases after about 680 BP, and cultural crops like cereals disappear. And this seems to be evidence of a period of landscape abandonment. It's at a time when there was Arab invasions of Anatolia and wars between the Arabs and the Byzantines. If that cultural collapse, if you like, was caused by climate, then it should coincide or have been preceded by a period of drought. And the purple arrows are showing drying trends. And what you can see from that is that the drying trends, the dry periods, did not occur at the same time as the pollen evidence for land abandonment. There's the dark age shown with the forest regeneration, but there is no shift in the isotopes indicating a drought phase either at the beginning of that or just prior to it. So that means that we can falsify the hypothesis that climate caused collapse in this case. Interestingly enough, however, we do see a correspondence in time between the recovery in human agricultural activity, the mid-Byzantine recovery, with an improvement in climate. So that there may have been a relation between climate and farming here, but it's a positive one rather than a negative one. So climate may, of course, have had indirect consequences, causes, but it wasn't the proximal or direct cause of the collapse. So time is getting on, so I'm going to come towards the last few slides and just really end by presenting a kind of very simple model that might help understand relations between climate and human populations over long time scales, that's to say over multi-millennium time scales. Now, of course, climate didn't change in the way that's shown in this graph, but nonetheless, we do talk about climate cycles, we talk about bond cycles lasting, 1,000 to 2,000 years. So it's not a totally outrageous idea to schematically show climate as alternating between, in this case, wetter and drier conditions over a time period of perhaps 5,000 or 6,000 years. If that was the case and that was a driver, then how might we expect human population to adapt? Well, the first thing is to show is that there clearly is a relationship in the way that I presented it here, but it's not a one-to-one relationship. First of all, there's a lag, and the lag in this case is something like 200 years, similar to the one that we saw for the Italian evidence. Secondly, there is evidence, I think, that population during periods of climate deterioration does not decline gradually, but actually falls more abruptly. So we've got a sharper fall in population. But the third difference is that at the end of each cycle, innovation creates a new baseline and a new level of carrying capacity for human population, so that the subsequent cycle, so we say the Bronze Age cycle following the Neolithic one, or the classical cycle following the Bronze Age cycle, starts from a new baseline and is able to support a higher population than during the previous one. So there's a long-term upward trend, even if over shorter time intervals, climate deterioration may have led to population decline. I'm not going to talk about the resiliency cycle of Holling and Gunderson, but many of you will perhaps see similarities here between their cycle, which talked about 4 different stages, including a phase of release and creative restructuring which is not dissimilar to the model that I've been setting out. I won't elaborate on this, but I just threw this in to add in that, of course, there are other complicating factors as well. One of them is the fact that as human populations increase, so they impact on environmental resource availability, on vegetation, on water, and therefore, if you do get degradation as a result of that, then that would actually reduce carrying capacity. We're not in a simple climate population system. Even if we just stick to environmental matters, then the environment itself is going to be dynamic and responsive. So if we look at the evidence for Mediterranean erosion, this was some data put together with colleagues and published last year, and it shows periods of increased erosion and flooding in different parts of the Mediterranean, and you can see in the pink at the top that although it fluctuates a lot, that there's quite strong evidence that erosion rates increased during the last 3,000 or 4,000 years, at the same time as tree cover declined based on the proportion of non-tree pollen. So that in turn then required human responses and adaptations. So, for example, if you lose soil, then that prompted new agricultural methods like terracing to conserve the soil. Okay, it's 3 o'clock in Italy, so I think I've spoken enough. So let me just conclude by a few bullet points to highlight the fact that there is clearly what you might call a normal set of relations between climate and population, in which favourable climate allows population to expand, but that those were interrupted, I think, by shorter periods, sometimes abrupt climatic events, sometimes more gradual, but periods at least when adverse climate led to new forms of human adaptation and innovation. And in many ways, in the very long term, I think we could see those crises as not so much a hindrance, but actually as a stimulus to social evolution in the long term. What is certainly clear is that human populations were capable and did expand in the face of, not because of, changes in climate. Technical, societal, organisation, adaptive responses allowed that to be the case. And I think in some ways we could argue that rather than, and this is perhaps an interesting conclusion in terms of current climate change debates, that in some ways perhaps resilience to climate shocks may have been less important than society's capacity to reinvent itself following periods of rupture due to some form of adversity. And then finally, just the technical point that if we are going to examine critically climate society relations in some kind of cause and effect way, then particularly for short-lived abrupt events, then we need to adopt approaches which allow us to do that. And I've highlighted a couple with Tephra chronology and the multiproxy approach. And I think it's critical that if we're going to draw wider conclusions, that they need to be based on approaches which are methodologically robust rather than relatively slack. Well, I think that's enough from me, so I shall say thank you. Grazie.
Thank you. Thank you very much, Neil. It's a great presentation, and I hope there is many questions for this very nice presentation, and also very wide. So in terms of from climate and the archaeological data and population and so on. So I think if people is interested in doing questions, you can see in the toolbars there is hands. You can just click on the hands and you can ask for the questions. Or if there is no so much questions, you can also switch on your microphone, and you can ask directly. So please, I see Piero Luninello. Piero, are you asking something? Yeah. Okay. Yeah. So you have the first one. Thank you, Piero.
And then I apologize because I have to leave. Fantastic presentation, really fascinating subject. It's really. I would like to be able to deliver such a nice. I would like to be able to deliver such a nice seminar on. So I say, well, it's really pleasant. That it's not so easy when you talk about climate. Anyway, we are often looking, in my understanding, to a sort of local relation, maybe in a broad regional sense. Can you hear me, or it is too quiet?
No, keep talking.
Okay. To an almost local relation, I mean, in a broad sense, you are looking to the climate in the Middle East, and you compare it with civilization in the Middle East. Climate in Anatolia, you compare it to climate in Anatolia. But climate is quite an interconnected issue, and especially we are talking about human societies. You can have a climate change somewhere else, triggering a movement of people, so that invasion, and then you get a change in a region that is not where the drought has occurred, for instance. Is it a relevant issue? Do you think you can have evidence for that in your analysis, or it's just a bit of a speculation that is not really substantiated by any evidence? Because we are having something similar now, you know, with change of global conditions somewhere else, because we are in a strongly interconnected system, changing affecting sector in a different place of the world.
Okay, thank you, Piero. Yes, I totally agree with you. I think you're absolutely correct. Particularly as society has become more complex, I think it's perhaps may have been less true, for example, in the Neolithic, but certainly once you move into complex societies and society today, then yep, the spatial interconnectedness I think becomes very important. I wouldn't disagree with your point at all. And of course, one of the ways in which there has been very rapid interconnectedness, which I didn't mention at all, is through pathogenic disease. I mean, we are obviously seeing it today with the coronavirus COVID-19 pandemic, but of course there have been other pandemics in the past which were generated in places remote from the communities who were affected. So, you know, in the case of the medieval Black Death, clearly that spread ultimately out of Asia and into Europe. And that was almost certainly the case also with the earlier plague of Justinian. There's been some recent work saying the impact of that plague was not as great as generally thought, but nonetheless it definitely occurred. And it could well be. There's been a number of studies done which have suggested that some of those pandemics had their origins in climate changes in areas remote from the human populations that were affected. So, you know, if you've got a disease which is carried, for example, by a rodent host, then rodent populations in areas like Central Asia, which today, for example, carry plague, and they do, if you had climate change in that area, it could lead to the spread of the population into other parts of the world. So, yeah, I mean, I think there's very many ways in which parts of the world have become increasingly connected, and it's not new. I mean, it's occurred in the past. So yeah, I would certainly agree with your overall point, with your observation.
Thank you. There is a question on YouTube. Bernardo, can you read, please, this one? Because I cannot see because I connect on Teams.
Yes. I would like to ask Professor Roberts if collapses of agricultural societies in marginal areas could be seen as a consequence of increased human pressure rather than of climate change.
Yes, but I don't think it is one or the other. I think it's the relationship between the two. So it could be that human population was increasing on its own, regardless of the climatic condition. But nonetheless, I think there's an expectation that particularly in dry farmed regions, where there's a direct reliance on rain-fed farming, that in those areas that the crop yields will depend on, and therefore food availability will depend on the prevailing conditions relative to the population that you've got. So I think, even if the climate was stable, the population would have to be restricted by the level of precipitation and the level of moisture that was available to support the crops. So even if the climate doesn't change, not climate change, but climate still is going to be a potential factor in limiting population. But what we also know in those dry farmed areas is that in practice, the climate does change. Just from the instrumental record, we know that the semi-arid zone has some of the very highest interannual variability in precipitation. And there's no reason to think that was any different in the past. So I think one of the questions for human populations and communities in those areas is, what is the level of population that you set? Do you set it based on the mean level of crop yield, or is it something above that or something below that? For a stable, resilient community, you almost certainly need the population to be set at a level which is not simply at the mean, but below the mean, because that will avoid crisis. In practice, I think a lot of human populations tend to drift up towards being above the mean, and that makes them, of course, vulnerable to any years of drought. So yeah, I think it's really the trade-off between climate on the one hand and population. It's not just a climate story; it's a population story too.
Thank you. Any other questions? Just give time for the reply. Neil, just waiting for others. I have a question to you. So I agree with you. One of the main concerns, in my experience at least, the chronology. It's of course one of the main troubles, especially in the Holocene, where probably also there is a very strong regionalization of climate. So different regions can develop also different conditions. So the correlation on records from very far environment can be also dangerous. But one point I think is still a trouble is probably, it's some climatic changes have some seasonal component. Yeah. So, and of course, like the general temperature we have shown at the beginning, so the 2013 temperature curve, it looks like more than a real temperature to the summer temperature. Yeah. So the point is, you think many of the example of climatic change you have shown can have different expression in terms of seasonality, or maybe they can show just dry condition, or maybe they represent more dry condition in winter. So, or what do you think?
Yes, of course, Gianni, you're correct. It's also true that it's generally pretty hard to get seasonal signals from our proxy climate data. I think we can do it. We can do it for, say, the last millennium. I think the tree ring record both has a very detailed chronology, but also in general, it's the way that the tree ring record is calibrated climatically is against the historic instrumental record. And that means that it's possible to use the instrumental record to look at which season of the year and which parameter correlates most closely with whatever you're measuring. I mean, an example which is just about to be published in Journal of Quaternary Science, for example, looks at the oxygen isotope content of tree rings in Britain. And there it was possible to relate it very clearly to, I think, summer season. There are cases where the climate data, I think, can be used to extract seasonality. I think as we move further back in time, it gets more problematic. What I think we can say, though, is that if we're moving back to the early Holocene, then the dominant forcing that actually led to the expanded monsoon and everything else was the precessional cycle. And the precessional cycle essentially changed seasonality. It meant greater receipt of summer solar radiation in the northern hemisphere, so in principle warmer summers and colder winters. So everything else being equal, you would expect that seasonality differences would have been greater the further back in time you go. I'm not sure that's been properly critically tested, but that would be the expectation. But of course, you're right that seasonality for human communities, it's not just a mean climate that matters. It's some very specific things that matter. Timing in the year is very important, and also whether good and bad years run together. Communities normally have no problem in dealing with one bad year or two bad years, but when you get 10 bad years, so the question is how far you get events clustering together in time. And there are some drivers. I mean, Tephra obviously is important for chronology, but it's also been a significant driver of climate as well. My personal sense is that even the big explosive volcanic eruptions are not likely to perturb climate. Individual events are not likely to perturb climate for more than a decade. So I find it hard to think that volcanic explanations would create long-term mega droughts.
Yeah. Single eruption probably.
I think they added short-lived things.
More than one. Yeah.
There's no evidence that I've seen that suggests that it's going to, change. That it could, for example, have created an event like 4.2K.
So I see Carlo Baroni has a question. Please, Carlo.
Thank you very much. I would like to thank very much Neil for his very nice presentation, very appreciated, and I completely agree with his. Most of his speculations, and particularly appreciate the concept of being taking care, being careful in correlating different proxies from different areas. There is a patch of different patches of condition, regionalization, and also seasonality that must be considered. So in many cases, interpretation should not be a switch on, switch off of the interpreter. It is a more complex question, and I really appreciate his presentation in this way. You think, but I would like to put a question. In some cases, for instance, if you look at pile dwellings, for instance, it's really evident that some kind of climatic condition can introduce or determine the abandonment of the pile dwellings and then the reoccupation during a second part of occupation of the same pile dwelling, for instance. So that is a climatic condition that must be considered at local, but the local for local significance, but possibly there is some connection between different regions with different pile dwellings, and then with the possibility in some cases to have a more than regional correlation. What do you think about that?
Thank you very much, Carlo. I think there are some instances where climate changes have more direct effects on human populations than others. Clearly, if climate change leads to flooding, then there has to be a response by the communities. Either you build higher houses, or you change your economy, or you move. Staying the same and doing the same things is clearly not an option. So in many ways, I think those kind of archaeological sites are some of the easiest to try and relate to environmental changes. And I think that's where I would personally expect to see some of the clearest relations or the clearest responses. But even there, I think societies had choices, and you know, if you've got a change in the environment, which means that your previous way of living can't continue, then you don't have to keep that same way of living. You can adopt other ways of dealing with it. And presumably some of the people who were living in the pile dwellings decided not to simply continue living in those wet environments, but went off into the hills or did something completely different. So I think societies always have choices. But I think the example you gave is a very good one of where we would expect to see local responses to wider climatic changes.
Thank you. With that, to continue with the second question, this is something similar, or can also try to relate to animals' response to climate changes. For instance, in Antarctica, penguins are moving, adapting, and occupying and colonizing different regions. That is a simpler way of moving and to adapt to new conditions. So there is some important correlation between human response and also animals' response, different animals' response to that. And that is possible a different way to try to correlating different information for different proxies.
Yeah, sure. I'm not sure I'm an expert on penguins, but I'll take your word for it.
Thank you.
Are other questions? So, are there any questions on YouTube channel? Bernardo?
No question.
So far. So, I don't think we can. I mean, we are not obligated to ask to ask questions. In any case, I want to say thanks to Neil, because I gave a very, very wonderful overview of different facets of climate, populations, and climatic changes. Also, you have time to give also in one reply about pandemic diseases, which have also now very popular in explaining some decrease in population, which might be also related to climatic change too. That's also interesting, an interesting field of development. As a last question, what do you think will be the future, for the future, to try to better define all these aspects? Which kind of approach would be useful, or which areas of the Mediterranean still need a lot of research? I've seen a very nice paper in review about Italy that I would be very happy to see I mean, the outcomes. But so, just as the last questions.
Well, I think I pointed a little bit when I talked about methodology and hypothesis testing. I think we do need to be more rigorous. Our science has tended to be rather inductive. In other words, we go out and we find a nice lake, let's take a core, here's a nice cave, let's go and investigate. And actually, science needs to do that first because you can't create hypothesis without some kind of background or evidence. But I think we now have probably plenty of evidence to create framework and to create interesting questions. And I think what I think would be good now is that we direct our field and lab research in ways that are more targeted to answering specific questions. So that may mean going back to some of the sites which we've investigated before, but analyzing them certain part of the record in more detail, or, for example, looking for crypto tephra, which we may not have noticed before. So I think we can advance the subject by taking the knowledge that we've got and trying to ask and test some questions in the ways that would be more rigorous. And some people would say, yeah, but geological sciences, archaeology and so forth, this is not real science because you don't have a laboratory with controlled conditions where you can do these kind of experiments. But I think there are ways in which we can, to use a very nice expression, coax history to conduct experiments for us. And I tried to highlight some of those ways, and I think we need to do a bit more coaxing of nature and history to help us answer some interesting questions. Anyway, that's just a personal view, but one to think about.
Thank you. I have a suggestions. All the people can switch on the microphone, and I think we can make a very big people.
Thank you very much.
And, for people who like statistics, or for us, we overcame 200 connections. So that's right. A really good, including YouTube and something like 60 in Teams and more than 150 on the YouTube. So it's really good. I see there are other last questions. I see just very last minute questions or not? No, it doesn't look. So Neil, it was really a pleasure. Thank you very much. A very nice number of people connected, also from outside Italy. That's also interesting. And yeah, so.
Okay, well, thank you all and stay safe, everybody.
You too.
I hope to see you in person, or many of you in person sometime.
Yes.
Eventually.
Who knows? Maybe in the field. Who knows? Maybe in the field. Thank you. Thank you very much.
Okay, thanks.
Ciao.